this is where we left off, and we were talking about the differences between cis and trans, and we said they had everything the same. They're almost like identical twins, except for the fact they are oriented in a different way. All right, well, there's more to the stereochemistry world, and we need to figure out what this is actually going to be. And one of the very first things that we need to have a discussion about in the world of stereochemistry is something called a chiral center. C-H-I-R-A-L. That is an R for those of you that cannot read my handwriting. I can't read my handwriting sometimes, so I know that you can't either. So we need to talk about what a chiral center is. It's just another fancy word that we like to use in organic chemistry to describe something pretty simple. So what is a chiral center? Well, most of the time we are going to be focused on chiral carbons. Chirality can be associated to many different things, but in the world of organic, as you can expect, we're going to be focused on carbons most of the time. Chiral carbon. Is this a chiral carbon? Yes or no? Here's a structure. Would you circle the chiral carbons in the structure? And I'm going to have to go through and circle all the carbons that I think are chiral. That is what this is going to basically be leading into. So the question that I have for you when we start talking about chiral centers or chiral carbons is, why can't you put the left shoe on the right foot? Okay? Why can't you put the right-handed shoe or right-footed shoe on your left foot? That's because your feet are chiral. There's a specific orientation. Your foot is made the same on both sides. Again, I hope. If not, that's okay. Maybe you have an extra pinky toe. I don't know. But for most people, the left shoe and the right shoe are identical, except for the fact that they are flipped. They are mirror images. And we get this whole concept of left-handed and right-handed form. The same way with maybe gloves. You have a pair of gloves, they fit on your left hand, and one fits on your right hand. You can't necessarily take the left-handed glove and put it on your right hand if it's made a specific way. So this is where this term chirality comes into play. There is a left-handed form of a molecule and there's a right-handed form of the molecule, and we're going to have to get used to this. We're going to have to get used of looking at structures that are drawn for us and picking out, is it the left-handed version or is it the right-handed version? I mean, I can look at you and watch you pick up a pencil with one of your hands, and just by that, I can identify if you are left-handed or right-handed. We need to be able to do the same with molecules. We need to be able to look at molecules and say, oh, you're a lefty. Or no, you're a right-hander. If you're a lefty, don't be like my kindergarten teacher and slap me with rulers just because I picked up my pencil with the left hand. She didn't like it. She wanted me to write with my right hand, so she came around and she whacked me with a ruler. Believe it or not, yeah, that's what I had to go through. Maybe that's why I turned out the way that I did. But if these molecules do have a left-handed or a right-handed version, we call these a chiral molecule. All right, so let me give you the proper definition of chirality. A chiral molecule or chirality basically means it is a non-superimposable mirror image. Okay, so the textbook goes through this whole concept of what chirality is and what a chiral center is supposed to be, and they talk about these non-superimposable mirror images, and then they basically give you structures and you just should be leaping bounds from there. Okay, well, if this is your first time taking organic, or, maybe it's been a while since you've seen chemistry, especially like this, then that's not going to work for you. Reading that text is going to be something very foreign language-y. But they at least probably give you a picture, and that picture looks something like this. And down here at the bottom, this is where I want to start. These are called achirals. Achiral means not chiral. Okay. Why didn't they just use non-chiral? I don't know. But achiral is the proper term. So, achiral objects. All right, well, if I take this chair, there it is, and I take the mirror image of it, well, this mirror image looks exactly like that chair, right? It looks like I can just take a pair of scissors and I can just cut this image out right there, and I could just take that image that I've cut out and lay it on top of that one without twisting, without turning, and folks, they will perfectly match up. That is what we call an achiral object. There are molecules that are achiral. There are molecules that do not have any chirality at all to them. They do not have a left hand. They do not have a right hand. That's going to happen. That's okay. The middle image has a picture of a fork. So what they tell you is, hey, here's a picture of a fork, and there you go. They take the mirror image of it, so they basically just kind of flip it around, and they say, now take a pair of scissors and imagine cutting that piece out. Can you lay that piece over this piece and have them perfectly match? And you can say, yes, I can. That's called achiral. They do the same thing with a glass over here, a typical drinking glass or a beer glass or a wine glass or whatever you decide to drink. It doesn't have to be alcoholic. Shame on you. Well, here we have a glass. We take the mirror image of it. That looks just like that. So surely I can take a pair of scissors and cut it out and have it perfectly overlap this initial image. I can do it. That is called an achiral object. Those we like. We don't have to worry about stereochemistry if this is the way that molecules come to us as. So we do have a proper term for those. Up at the top, you see 3 more images. All 3 of these images are chiral ones. All right, so that means if I take the mirror image of it and I take a pair of scissors and I cut out that image, can I get this to overlap? And the answer here is no. Either one of these cases, you're not going to be able to do it. So here is the right hand. I'm going to take the mirror image to get the what we know is a left hand. Well, I take a pair of scissors, I cut this out, and then I take this hand and I try to overlap it over here on this one, and there's no way that I can flip it. Even if I flip it, I can't get it to match, because if I did flip it, what's on the back side of this? It's the palm. It's the back side of your hand. This is your palm. If I flip this around to get my thumb and my fingers to match, folks, I've got a different surface on this side that I have to worry with. They are not going to flip around and match perfectly. The same thing happens to your ears. Can't do it. The same thing happens to the seats in your car. Look, here's the steering wheel, and there's where your passenger sits if you're in the United States of America. You flip this around, there's your mirror image. I cut this out. Is there a way that I can turn or twist or do something to make this perfectly match? And the answer is no. I cannot do it in either case. These are chiral objects. The mirror image does not match the original. There's no way that I can get this thing to cut out and overlap without causing me an issue. Now, let's do an example problem. Name 5 capital letters that are chiral, and then name 5 capital letters that are achiral. So the easiest way to do this, people, is just to go with the alphabet and start there first. So let's start with A. Okay, so here's capital A. Now take the mirror image of it. Okay, so if I take the mirror image and this side goes over here and that side goes over there, I end up with something that looks like this. Do those overlap? Yes, they do. They overlap. If they overlap, then this is called a chiral. There's my first one. Bing, bing. Got it. Now let's take a look at B. I'll draw this one down here. There we go. There's B. I take the mirror image of it. This left-hand side comes over here. This side goes there. Can I take a pair of scissors, cut that out, and stack it on top of that one and make a match? Can't do it. This is a chiral molecule. And in this case, a chiral letter. Okay, well, what about C? Well, C's there. I take the mirror image. It goes like this. There's no way I can take a pair of scissors, cut it out, and just shift it across and make it overlap on top of that one. I can't do that. So therefore, this is chiral as well. If I take a look at D, there's D. Take the mirror image, straight line here. There's the curve. Cut it out. Can I get it to perfectly match that one? The answer is no. Therefore, that is chiral. If I take a look at E, well, there we go. Cut it out. Can't make them overlap. That is also a chiral molecule. F is going to be chiral. G is going to be chiral. So it told me 5. I'll stop with F. There we go. There's that one. H. Finally we get one that's going to perfectly match. Just like A did. So that's a chiral letter. I. Okay, I can take I. I can flip it around. I can cut it out. They perfectly stack on top of each other. J, not going to do it. K, not going to do it. L, not going to do it. M, look at here. Take the mirror image, stack it on top of each other. There you go. There's my 4th. N, not going to do it. O, as you can imagine, mirror image, perfectly stacks on top of each other. So folks, we just answered that example problem together. Now, you're probably asking, why am I torturing you with this stuff, right? Maybe just not stereochemistry, but maybe with organic as a whole. And that I can't give you an answer to. Somebody at some point in time said that organic was a great choice for you. So you listened to them and you took the class. But I hope that you're having fun. I enjoy you while you're here. So the issue here is, why is cis and trans and why is stereochemistry such an important thing that we do stress? And a lot of people lose focus on these types of things because they're so focused on just answering problems the right way that they lose sight of the real thing. Well, the problem here that we experienced was in the mid-50s. So 1950s, we get a drug, and that drug is called thalidomide, and it was approved as a sedative. Well, sedative typically for people that needed to kind of chill out for a little bit. But at the same time, it was also prescribed to pregnant women. It worked extremely well for morning sickness. And this drug was made, the drug was tested in other countries. It was passed. It was not passed in the United States. The FDA in the United States basically said, you know, I think we need more studies on this drug, and we're just not really comfortable releasing it yet. But if this is something that your country wants to do, then by all means, go ahead and prescribe it. We're not going to tell you what to do with your people. So thalidomide was approved as a sedative, not in the United States. It was given to many people, and it was called what we say a racemic mixture. All right. So racemic is going to come from the word racemate, and this means a mix. So this was a mix of left-handed and right-handed forms of a drug. It worked extremely well, but they were giving it to pregnant women during that time. It was actually kind of curing their morning sickness. They weren't feeling nasty and disgusting in the morning, or they didn't have these throw-up episodes. You know, people loved the drug that was taking it. It worked extremely, extremely well. The problem that they did not know at the time, though, thalidomide, it was the same number of carbons, it was the same number of hydrogens, it was the same structure. It wasn't a constitutional isomer. It was just different in the 3D orientation that it was made. That was the only difference. And it was really before we understood the importance of left-handed and right-handed forms of drugs, especially drugs. And what they discovered is that the levorotatory, this is the L form, left-handed, it was highly mutagenic. It caused deformities. It also led to cancer problems. Folks, this drug was approved by governments. The government said to doctors and physicians, it's okay to give it, especially to pregnant women. Help them out. They go through enough. Physicians were prescribing it to patients left and right. These patients would go to the doctor and they would trust what their doctor was telling them. And the doctors were trusting what the government basically told them to do because they said it was safe and the physician said that it was safe. And a patient is going to trust them because that's what they went to school for, right? Well, over time, what was happening were things like this. This is what thalidomide did. This is what cis and trans did. This is what stereochemistry did. This is what R and L did in the pharmaceutical world. You want another picture? Here's another. This is organic chemistry here, folks. This is organic chemistry before it was fully understood by governments across the world and approved and stamped safe to use for various things, various ailments, various symptoms. It was okay. You want another picture? Here's another. These are what we call thalidomide babies. And this was the common theme throughout that time. If your mother or was pregnant during that time, and if she was prescribed thalidomide during this time, these were some of the things that were happening. And it wasn't just like a little bleep. It wasn't something that was happening just one time only, or there were just a few incidents of it and that was it. It was pretty common. And it was all due to organic. How? Here was the thalidomide drug. To the left and to the right, you're seeing the R and the S form. Otherwise, later on down the road, you're going to be calling it the D and the L. One left-handed, one right-handed. Completely different properties. What was happening is that the studies that were done on this one. When the drug was manufactured, well, there was no control in the manufacturing aspect, and the drug was getting manufactured, the drug was getting made. There are very similar characteristics between these two other than the 3D fashion that was going on with it. So when they prescribed the pill, they actually took both of these and they mixed it together and they put it into a pill thinking that they held the same properties. And only until after the fact did they realize that was not the case. They're completely different. The FDA in the United States now requires all manufacturers of drugs, every one of them, to provide reports on every single chiral center or stereoisomer if the drug is going to be sold and manufactured as a racemate or a racemic mixture. Every carbon, folks, every carbon. If there's more than one carbon in the molecule that is chiral, then that carbon can have a left-handed, right-handed version. All of the other carbons can also have a left-handed, right-handed version, and all possibilities have to be tested independently. And people wonder while the pharmaceutical drug industry is spending billions of dollars in the research of a new drug. This is one of the reasons. Most people don't realize that. Most people think that pharmaceutical companies just come up, bring a new pill out of the underwear, and say, here you go, take it. That is not how this works. In order to make a pharmaceutical drug, maybe a better drug than what's on the market, these pharmaceutical companies have to spend billions of dollars, not only in the research and development side, but in the production side and in the regulatory side as well, just to get it approved through the United States government. All of that is important. All of that are studies that have to be submitted. All of that is proof and justification of why it is okay for people to take this pill that your doctor wants to give you. Sometimes things slip through. Sometimes mistakes are going to happen. That's just the way it's going to be. No, nobody's perfect. So, these pharmaceutical companies have to spend billions of dollars to get a drug approved. What do you think they're going to do? They're a business. They got people to pay. They've got payroll. They've got paychecks to give to people like you. People like me, maybe, that work in a lab. All of these people have to get paid. They have to make a profit. If you're not making a profit with a company, then why are you in the business for? So they turn around, they sell a drug for hundreds of dollars a pill. They've got to reclaim their money back some way, some form, some fashion. They ain't going to make it for free. They're not going to give you a pill for free. They're not in it to make free things. Somebody's going to have to pay for it. No such thing as free, especially in the pharmaceutical world. Zoloft and Paxil, these are two of the bigger kind of pharmaceutical drugs that people maybe can associate with. They are what we call single enantiomers. All right, so in enantiomer, you're going to see this word a little bit later on. We're going to talk about what this word means. So that's to come. Don't freak out on me yet. And they're doing much better market-wise than something like Prozac, which is a racemate. So Prozac is an enantiomer, and it involves the left-handed and right-handed forms. However, Zoloft and Paxil, very similar, but yet they are what we call enantiomer pure. One or the other. You don't get a mix. So the question that we have to have at this point, we're going to have to be able to look at molecules like this, maybe not this complicated at the beginning, but we're going to have to be able to look at molecules that are drawn that way, and we're going to have to be able to determine, are those R's or are those S's? Are those left-handed or are those right-handed? Are those D's or are those L's? I'm giving you a lot of one-letter abbreviations, and we'll get familiar with each one of those. Just bear with me. But we're going to have to identify it as the left-hand or right-hand form. And the reason that this is so important is because we want to prevent these things from happening, right? We want to prevent that from happening again in the future. We want to prevent these types of things from going on in the pharmaceutical world, because the last thing that we want to do is to give someone a pill that we don't know all of the details for, and for this to happen all over again, right? So this is the power of organic. It's the importance of organic, and it's why we talk about the things that we talk about. So in the next video, we're going to pick up with the term chiral, and we're going to start looking at very simple molecules and talking about how to identify chiral carbons, if they have any, and then if they do have any, how do we know if it's the left-hand or right-handed form? Because as we saw, thalidomide was a disaster. Were there others that could have also been a disaster if we didn't wise up and discover the difference between left hand and right hand? Maybe.